Today I show you a few interesting things about my favorite amino acid, which is cysteine. Cysteine plays a pretty important role in your body because everything that's made of keratin, like your nails or your hair, contains L-Cysteine. D-cysteine doesn't play an important role in biology. And that's a molecular structure of it. You can see the part that you find in every amino acid, and it also contains an SH group. And this SH group can be oxidized to make disulfide bridges, and that's what we're going to try later. You can easily get cysteine if you buy it as a nutritional supplement. I got 500 milligram capsules, 60 of them, for around 10 bucks. And I was pretty lucky because inside of the capsules there's just pure cysteine, and only the shell of them contains some other chemicals, like in my case it's gelatin or iron oxide as a dye, and that's a pretty good thing. It should be pretty easy to open the capsules. You just have to pull on both sides of it and then they're open. That's it. That's how the cysteine out of 5 capsules looks like, and I'm not sure if you can see it, but it forms long and spiky crystals. It's not a powder as I thought it would be, but yeah, it's crystals. Let's see if it has the same shape if we oxidize it. What I'm doing now is oxidizing the cysteine crystals with hydrogen peroxide. So that's just 30% hydrogen peroxide. It might be a bit overpowered, but at least it will work. Now just stir a bit, and then you will already see that the disulfide bridges form, because it's not crystalline anymore. It gets suspension, so it becomes a powder. And if you do it, just wear some gloves in order to protect your hands, and you will find out that it smells a bit like H2S. I don't know why. There shouldn't be a gas produced, but whatever. Now this is what happens if you don't pay attention and the temperature rises too high. I think it was a kind of caramelization reaction or something, so there's carbon which is produced, and what I wanted to do is just to evaporate the water and the hydrogen peroxide out of this suspension to get the pure disulfide bridges bonds of the oxidized cysteine, but without any water, to compare it with the normal cysteine. And yeah, now that happened. Now this is the normal cysteine, which I oxidized with hydrogen peroxide and evaporated all the water and the hydrogen peroxide remaining out of it, out of the suspension, and it became paste-like. It's not crystalline anymore. It's like a paste. I couldn't get more water out of it, and that's because of the disulfide bridges. And this happens if you use too much hydrogen peroxide and when you heat them up, the suspension. So I got a kind of carbon snake, which I didn't want to happen. So what I think is that this is one more state of oxidation, but I'm interested in this one. Now let's have a look at the mechanism of this oxidation. So we have our cysteine molecule, and if we take 2 of them, it looks like this. That's a R is the rest of it. Then we have those SH groups. If we add some hydrogen peroxide, the sulfur gets oxidized, and what we get is disulfide bridges, which look like this. And what I think what happens with the remaining hydrogen atoms is that they that the hydrogen peroxide gets reduced, and together with the hydrogen atoms of our SH groups, we get 2 molecules of water. But I don't know if this is right, because I kind of invented this experiment myself, but that's what I thought what happened in this reaction. Now let's have a look how good both forms are soluble in water. So that's just a normal cysteine, which is not oxidized, and is oxidized paste-like cysteine. I'll add some distilled water. It's around the same amount, and I'll just mix it a bit. And as you can see, the normal form of cysteine, which hasn't been oxidized, is much better soluble in just normal water compared to the oxidized form. And I think that this is because the normal cysteine is like an alcohol, because of this SH group. It's pretty polar, and polar molecules are soluble in water, and the disulfide bonds or bridges aren't very polar, and so they don't dissolve in water. I'm not sure if this is right, but I think so. As you can see now, after stirring it a bit, everything dissolved here in the left container, in the normal cysteine container, but here it just became a bit milky-like, and there's still the paste down there on the ground. Yeah, I hope you like this video, and see you next time.